Welcome to the second video for the 6th class session of instructional videos. In our first video we looked at a rotational diagram for ethane. We considered its staggered and eclipsed conformations. And we saw how the staggered conformation was lower in energy than the eclipsed by about 2.9 kcals per mole. And we asked, why is the eclipsed form higher in energy than the staggered form of ethane? And the answer that we gave in our first video was that there was repulsion between the hydrogen atoms bonding electrons in the eclipsed form that could not be found in the staggered form. So one word summed this up, it was sterics, or steric repulsion. There's also another reason that the staggered form is more stable than the eclipsed form. That reason is something called hyperconjugation. So there's a icebreaker for parties. Hyper means through space, and conjugation means overlap. And this effect describes the interaction of a filled bonding sigma carbon-hydrogen molecular orbital with an empty sigma star antibonding carbon-hydrogen molecular orbital. That interaction stabilizes, that is, makes lower in energy, the staggered conformation. So you can see how in the staggered conformation we have bonding electrons from the sigma carbon-hydrogen molecular orbital with the same phases on the same side as these lobes of the sigma star antibonding carbon-hydrogen molecular orbital, which is empty. And this close proximity allows there to be overlap, that is, shared electron density, electron donation from the bonding molecular orbital to the antibonding molecular orbital. Of course, it's a small effect, but it's something that is more and more experimental evidence lends credence to. And so this is versus the eclipsed conformation, in which, even if we had the correctly phased relative orbitals, there would be poor overlap because of the geometry. We'd have the large lobes pointing away from each other and only the small lobes pointing toward each other. So in the eclipsed form, the interaction of the filled bonding sigma carbon-hydrogen molecular orbital with the sigma star antibonding carbon-hydrogen molecular orbital is poor. So we would next need to ask ourselves, what could we do to complicate our lives in terms of a model for this? And we could say, well, why not add one carbon to our ethane and see what we could get in terms of a rotational energy diagram. So we've come up with this molecular model of propane, a nice 3-carbon molecule. Now if we were to cite down the C1-C2 bond, we could see, oh, this is a staggered conformation of propane. Of course, we could rotate around that carbon bond, that C1-C2 bond, and we could rotate to an eclipsed form of propane. So we have 2 hydrogen eclipsing interactions, and then we have 1 hydrogen methyl group eclipsing interaction. Again, we can keep rotating, and oh, lo and behold, we're back to a staggered conformation of propane, which would be, we would think, similar in energy to the first staggered conformation that we looked at, because it's simply rotated and looks the same. So let's look at that on two-dimensional paper. And what do we see? Let's try propane. So here we go. The view that our eye sees is the 0 degree view. So the methyl group is pointing straight down, it's staggered. between HA, which we would see pointing down and to our left, and the hydrogen that has the dashed bond, which points down and to the right. And of course, this hydrogen points straight up. Of course, we could think about turning the back, or excuse me, in this case, we turn the front counterclockwise 60 degrees to go from the staggered conformation to the eclipsed conformation. If we keep turning that front carbon like a propeller another 60 degrees to a total of 120 degrees, we reach another staggered conformation. This time HA is down and to the right. And so if we looked at an energy versus rotational process diagram, we would see a very similar pattern as we observed for ethane. The only difference would be the energy gap is higher. So the energy barrier to rotation is 3.2 kcals per mole versus ethane's 2.9 kcals per mole. And we know that this is reasonable because a methyl group is bigger than a hydrogen. So there's a greater steric interaction in the eclipsed form. There's still very free rotation though. And so this brings us to the question of how can we complicate our lives further and study this energy versus rotational process with a nice simple model system, which could be used as an analogy for other conformational problems in organic chemistry. And of course the answer is we would add one more carbon to our carbon chain, and we would look at the rotational process for butane. And so that will be the subject of our next video segment.